All right, we got any questions before we get started today? Homework number 2 was due right now, so hopefully you guys have submitted that already. Homework number 3 is going to be assigned on Monday because we have that slight delay. Technically, I could assign it to you after this class today, but it'll be up on Monday, I think. So we are now at, okay. What happened to, I thought you guys had no questions. All right, what's up? It's always 1 week, yeah. Is that your question too?
And is the exam still on the same time?
Don't trust the syllabus. Trust me, the exam is going to be 1 week after homework number 3 is due. I'm pretty sure that's when it's going to be. So we will talk more about the specifics for that when we get closer to it. Okay? Oh, yeah. So on Blackboard, some people are having trouble with submitting to Blackboard. So there is like a test assignment submission up there. You guys don't need to worry about that too much unless you want to use it to like troubleshoot why you can't submit on Blackboard properly. Okay. When will it be due? I think we just answered that, but the due date is also on the documents themselves. All right. Any other questions? Okay, let's get into our next topic for this class. First and second order systems. I think it's in chapter 4 of the book, but I'm not 100% sure on that. So what we're going to cover today, we're going to cover 2 of these topics. The first one being poles, zeros, and system responses. Then we're going to talk about first order systems. From there, we're going to get into types of second order systems. Then we have the general second order system that we'll talk about. Hearing a lot of whispering today. What's going on, guys? You guys were super quiet when I first came in here. Now it's just constant, or maybe I have tendinitis. I don't know. One of the two. Underdamped system characterization. And approximating systems as second order. Right, a lot of these topics should be familiar with you guys as well. Maybe we'll get some new perspectives on this. So today the plan is to talk about these first 2 here. And the first exam will cover up at least through these 2 topics, maybe even these ones here, or even this entire section, but we'll see. Probably just the first 2. All right, so poles, zeros, and system response. So let's say we have a generic transfer function, y of s over u of s is equal to, let's call it g of s here, or a numerator over a denominator, right? We're going to write it in a slightly different form than we normally deal with here. Instead of doing the polynomial, I'm going to factor some things together here. Let's actually go with a minus. S minus z1, s minus z2. And that can go on and so forth until we get to s minus zm, where all these z's are constants. Similarly, we can have something on the bottom here. Right? These are all multiplied by each other. Right? So all zi and pi, or pj, I guess we can call them, are constants. All right, so can anybody tell me what the definition of a pole is for a transfer function? What is a pole? What? A root? Okay, root of what? So root is going to be a key word here. So I like the direction you're going with here. Root of what? So numerator or denominator? Denominator, right? So values of S that make G of S go to infinity or the denominator go to 0, right? Are poles. That's a technical definition for what a pole is. Right? It's setting our transfer function to infinity, right? These are often the roots of the denominator. If you know you set up everything in that proper polynomial form, right? So the poles here, that's found by setting that denominator equal to 0. In this case, it would be P1, P2, all the way to Pn. We would have n different poles for this system, right? What about a 0? What's the definition of a 0? Speak a little bit louder for me. Roots of the numerator, right? Values of S that make G of S go to what? Go to 0, right? That's where the name comes from. Right? Often roots of the numerator. Zeros here, set n of S is equal to 0. You would get Z1 all the way through Zm, right? These are our zeros, right? If you want to think about it, this isn't, really accurate, but let's just pretend for a second, right? 5S on the x-axis, and how do I close this thing at the top again? Dialight. Press a button and see what happens. Forget it. All right, so if we have anywhere there's a pole, the value of G of S is going to shoot off to infinity, right? Anywhere there is a 0, GS goes down to 0, right? Something like this, I guess, is what we could draw it as. Right? This would be a 0 of G of S. This would be our pole, right? Those values of S there. All right. There is an exception. To both of these rules. Right? If any roots of the denominator equal a root of the numerator, what would happen? Let's say we have G of S is S plus 1, and S plus 2 down here, right? What are our poles and what are our zeros in this case? Pole at -2, right? Will we have a pole at -1? Will we have a 0 at -1? What do you guys think? How many think we would have a pole at -1? 0 at -1. They don't count. The exception, right? This is the exception, right? They would be a pole and a 0 here, right? Even though it doesn't set it off to infinity or sets it off to 0 here, these would both still count, right? So we would have both a pole and a 0 at -1 here, right? So what that means is that you don't cancel out poles and zeros, right? That is our exception to these rules that we had above here, okay? So let's go through an example really quick. G of S is equal to S plus 2 over S plus 3 times S squared plus 36. All right, tell me what the poles and zeros are here. How about folks online, tell me what the zeros are. I'll give you the easy one. Folks in class, tell me what our poles are. So folks online, S plus 2 is equal to 0. So our pole, or our zero rather, S Z1 is -2 in this case. Nice and easy. Right, the values of S, the roots. Poles, what we got? -3. Okay, is that it? Right, poles and zeros can be complex numbers, right? Or imaginary numbers or real numbers. All right, we need to keep that in mind here. That's found from S plus 3 times S squared plus 36 is equal to 0, right? Solve for S, those give us our poles here, right? So they can be real, they can be imaginary, they can be complex. Very often, we'll draw in this class the real and imaginary axes here, right? The sigma is going to be representative of a real part of a pole. J omega is representing the imaginary part of it, right? And so if we wanted to, we could plot our poles and our zeros in this little figure here, right? These would be our two poles at plus or minus 6j or 6i, right? We have a 0 at -2 and a pole at -3. Zeros are represented by circles typically. Poles are represented by an X. Right, we're going to use this a lot in this class. Right, if we had a complex pole, where would that go in this figure? Complex pole. So what does the y-axis represent? That's the imaginary part, right? In any of the quadrants, right? You could have a complex pole out here, or maybe there's a 0 over here. We'll get into that a little bit more. It depends on what quadrant, but it'll end up being in one of them at least, right? Okay. So now, let's say we have a specific input for our transfer function, and we want to figure out what y is. What will the output's response be? Right. So I have an example here. Y over u is equal to G of S. That is S plus 2 over S plus 5. Right. And then I'm going to say U, or U of S, is a unit step. What's a unit step? Since I feel like a lot of you guys need to review this again. What's a unit step? Get in Laplace world. Give it to them. You guys speak louder, and you're not even saying anything. You're literally just mouthing it. 1 over S, thank you. I knew you had it right, you just need to actually say it, right? How can we solve for y in this case? Right? We separate y out from the rest of it. Right, and then we would do an inverse Laplace transform, right? May need to do partial fraction expansion here first to do that. So y of s would be s plus 2 over s times s plus 5. If you did partial fraction expansion, you'd end up with 3 over 5 s plus 5 plus 2 over 5 s. I think that's what it would end up being. All right. So the question becomes, what are the poles of y of s due to the natural dynamics? And what are the poles of y of s due to the input? We want to call these poles here. What are our two poles in this case? What are the values for them? Where do we find poles? Roots of our denominator, right? So what are our poles? -5, where's that go? Is that due to the natural dynamics or is it due to the input? Natural dynamics, right? That was part of our transfer function. Right? What about P2? Right? That's due to our input, right? We have a pole at 0, right? That would shoot off that term to infinity here, right? So that's from the transfer function. That's our natural dynamics. So that's from the transfer function. And that is from the input. All right, we could go through and solve this. Y would be the inverse Laplace transform of y of s. It's 3 over 5 e to -5t plus 2 over 5. It should just be 2 over 5, right? Over here. Right? This is due to g of s. And this is due to the form of u of s. Right? We're not really going to focus too much on this class on poles that are relating to our inputs. At least we're not going to pitch it that way, I guess. But what we will talk about is that our output has two responses in it, or we can break it up into two responses. The first is the natural response, and the second is the forced response. Right? Terms you guys should be familiar with, right? Natural response is what the output would do naturally due to the dynamics, due to the poles of g of s, right? The forced response is due to the poles of u of s. It's due to our input, right? Our forcing term that's trying to change the system, right? The zeros, they just change what our output would end up being. Like scaling it. Right? What's another way that we could break this up into another set of two responses, different categorization that you guys should be familiar with? We've actually talked about it already. It was in the first homework. It's another way to categorize this. Steady state, all right, very good. So we have a steady state response. Right? That'd be the thing that's left over when time approaches infinity, right? What's the other one? What's the other half of it? This is steady state. What's the other piece? Transient response. Very good. Right? That's the stuff that changes over time and usually dies out if you have a stable system. Right? Which I'll say for now, assuming stable system for now. And we'll get into stability in a little bit. All right. Any questions on this? Should be familiar with you to you guys. All good? Then let's move on to first order systems. How many poles do you think a first order system would have? I'm talking about the transfer function. What do you guys think? Am I asking a trick question or not? That's probably what you guys go through normally when I'm asking something. First order system, how many poles do you think we have? Just one. First order system. How many zeros? What do you guys think? One. So I see a one. Any other guesses? Does zeros have to do with anything with the order of the system? No, right? So technically, well, sort of, we could say that there are an infinite number of zeros, right? But it's got to be either 0 or 1 for us to deal with physically realizable systems. So first order systems, we have one pole in the transfer function, and we have 0 to 1 zeros in the transfer function. All right. Can the pole, right? So we can have complex poles, we can have imaginary poles. What do you guys think? Where is the pole for, and even the 0, where is that going to exist on this real and imaginary plot for a first order system? What quadrant, what axis? Where do you think the pole is going to be? Has to be on the real, exactly, right? We have a first order system, right? We cannot have a pole that has any imaginary parts to it. Imaginary parts always come in pairs, right? It has to do with that square root of a negative number, right? So if you have an imaginary pole, you're probably going to have 2 of them. Same thing with zeros, right? So this will be on the real axis. Makes it very easy to analyze as a result, right? So for a lot of this, we're going to look at the step response of a generic first order system, first order transfer function. Because this is going to provide a lot of useful information to us, right? So a generic first order transfer function, and I'm going to say there's no 0. So we don't have any zeros in this one. That's going to be y over u. We can write it as b a over s plus a. Right? You could also just put b over s plus a. That would work as well. But we may end up using the form that we have there to simplify things in the future. We're going to assume for now that a is greater than 0 and b is not 0. Right? Again, a is greater than 0. We're assuming that our system is stable, which we'll talk about eventually. Right? We have a unit step for our input. U of s is 1 over s. Our pole of g of s, right? When I ask for poles, I'm always asking for transfer function poles, not for the inputs. That's usually not as interesting to me. So our pole, we set our denominator equal to 0, right? What's that called? You guys remember when we said our denominator equal to 0? What's that equation called? It has a specific name for it. Say it. Characteristic equation. Very good, right? Setting the denominator equal to 0. That is our characteristic equation. See someone in the chat got that as well. Excellent. Right? So S would be equal to negative A, and that's how we can figure out what our pole is. P is negative A in this case. If we wanted to, we could plot it out on our imaginary and real axes, and it'd be somewhere over here, wherever negative A is. That's where our pole would exist. Right? We can also go through and get a solution to the output, right? Very similar to what we were talking about before. Y of t will be equal to the inverse Laplace transform of y of s, right? Which that is g times u. We already said what g and u are. Right? And we could go through the math. I don't think it's necessary in this case. But u was 1 over s, g was ba over s plus a. And we can do an inverse Laplace transform, and we'd end up with b times 1 minus e to the negative at. That's what we would end up with if we went through this. Right? So, assuming b is non-zero, and a is a positive number, if I were to plot our output versus time, what would it look like? Can you guys just describe that to me? Where's it going to start? Where's it going to end? Start at 0. Okay. Why 0? Let's just plug in t is equal to 0, right? What happens when t is 0? What happens to that e term? Just becomes 1, right? This becomes 0, right? What's going to happen after a very long period of time? Let's say t approaches infinity. What happens to that exponential then? It'll go to 0, right? Because we have a negative term in there. So what should y turn into? It'll turn into b, right? So what we should have is some sort of exponential leading up to b, right? That's what this is going to look like. That's our first order system response to a step input. Right? And we can describe this pretty much with just our pole and that b value there, our steady state value, right? Those are the only two things that we really need to, and then we know it has to deal with an exponential from there. All right? But now, instead of describing things in terms of a pole, I want to introduce a new parameter to describe our system. For first order systems, how many of you guys have heard of the time constant? Show of hands. Hopefully everyone here should have heard of a time constant. If not, in 3333, I mean, I think it even shows up in heat transfer and stuff like that, right? Our time constant in this class is going to be defined as tau, is how I'm going to usually represent it. It'd be 1 over a in this case, or negative 1 over our pole for a first order system. With p being less than 0. So if our pole is negative, we can have a time constant, right? We have that solution y is equal to b 1 minus e to the negative at, right? Or b 1 minus e to the pt, right? That was our pole. We can also write this as b 1 minus e to the negative t over tau, right? That's another way to write out this problem. It's probably one that you guys have seen before, right? So what are the units for our time constant? Right? It's a time constant. It's going to be in seconds. right? What about the units of a pole? Was it? Right, pole and our time constant are the opposite, right? So it should be 1/seconds, or it's like a frequency, right? So that's our connection, that 1/s or 1/seconds here. Right, I'm going to use this to represent seconds and not s, right? But this CNC, our s's, our poles, they are relating to frequency somehow. That's why you guys see that Laplace domain solutions are sometimes called like, or Laplace transforms are transforming into the frequency domain. Has to do with that connection there. Okay. Going back to our time constant, right? Time constant tells us how long it takes to go from our initial value, 0 in this example, to approximately 63% of the way to the final value. The final value being B in this example. Right, so if we were to plot this out, again, the same thing as before, y versus time. Right, and we had a curve that went something like this, right, where this was B, right? If I broke up my time axis into, let's say, this isn't going to be totally accurate, but that's 1, 2, 3, 4. This is going to be tau, 2 tau, 3 tau, 4 tau. This value right here should be 0.63 times our final value, right? This is what our time constant represents. 63% of the way there. That's 0.63 times B. Right? So based, why 63? Go through and analyze, has to do with the exponential itself, if I'm pretty sure. So if you like analyze what an exponential will do, the variable that's multiplied, or I guess the inverse of the variable that's multiplied in that exponential by t, will factor out to get to 63% of the way. It's essentially has to do with the decay of an exponential. Other questions? I don't think we're talking about a stochasm here, right? This is all
No. Here, the same. That's 63%.
maybe, but I guess I wouldn't. 63%. Well, what do you mean by 63% of the data, right? Because if I run this for
63% of
okay, so that has to do with the definition of, I'm guessing, Gaussian noise, which has to do with an exponential. I think there is like the error function, as I think relates to it, that has some sort of exponential factored in there, right? But that's because the noise terms, if I recall correctly, it's been a while since I've looked at it, relate to exponentials. Exponentials are like a fundamental, like one of our fundamental like functions that we have that exist in this world and out there, right? Kind of like a sine wave or a cosine wave. So it's the opposite direction, I think, of what you're thinking about. It's, I think the probability stuff, it's because it comes from this exponential, that core one. That would be my guess. That's an interesting question. I've never gotten that one before. Okay. All right. So how long, based off of this graph, how long does it take to get to B about? Our value of B, approximately. Well, how long does it truly take to get to that value of B? Infinity, right? So now let's go with approximately. How long will it take there? 4 times tau, right? What is that called? Sometimes I'll write this as big T of S. What is 4 tau? The time it takes to get to steady state approximately, right? There's a name for it. Was it? Well, it is a transient characteristic. You're correct about that, right? Settling time, right? That's why there's an S there. Yes. So we have our settling time, right? Relates to our time constant for a first order system, right? Amount of time it takes. Let's say amount of time it takes to get within about 2% of the final value. Right? That's our settling time. That's another parameter that's going to be relevant for us. It's another way we can describe our first order systems, right? So our first order systems can be described by the steady state value, right? That factors in to some extent, right? It could be described by our pole. It could also be described by our time constant. It could also be described by our settling time, right? And then there's one more that I don't like to use a lot, but the book keeps pulling it up. That's called the rise time. And for a first order system undergoing a step response, right? This is all for step responses here. That would be about 2.2 times tau. The rise time is the amount of time it takes to go from 10% to 90%. Right? The amount of time it rises. Personally, I think it's kind of a dumb definition, but does factor in for some systems. You may want to define things in terms of its rise time. All right, any questions on first order systems up to this point? No questions? All right, so I have a question for you guys. Why is this useful? I think could be approximated as exponential. Okay. All right, getting closer to something. Is there not one for 100%? For a rise time, typically rise time is defined as 10 to 90%. I could say maybe 10 to 98%, but for 100, that would be infinite amount of times for an exponential. Is a way to measure performance of terms in time, I think you're getting close to something there. Other ideas? Any other brave souls that are willing to take guesses, right? You guys are seniors, right? You probably want to be at the stage where you're learning something that could be useful, right? Why is this useful? Sure, that could definitely factor in, right? All right. Any other ideas? I mean, these aren't necessarily right or wrong. Good, right? We'll get into that. That's control, right? So absolutely, we can adjust our system, right? If we have some things that we can control to make sure we get to steady state by a certain amount of time, right? That's characterized by our time constant. Sure, it could be for frequency-based operations, but that'd be more like sinusoidal inputs if that you're thinking in terms of that. But yes, using the frequency domain can certainly help. Population growth. Yes, it could be used to model that, depending on the dynamics that you actually have for it. But that's talking about like actually getting the model itself, and then I guess predicting it, right? What about, have you guys heard the term parameter identification before? Yes, no? No, what about model fitting? All right, these to me are more or less the same thing here. So let's go through an example, and this will be it for today. So I have a battery, right? Literally have one in my lab. I probably should have picked one up. Let's come over here. But I want to get a mathematical model for the battery, right? I want to get a representation similar to what we were doing earlier in the class, right? Something that's going to represent that battery, right? I'm going to assume the battery can be modeled by a first order transfer function. This is a terrible assumption, but we're going to go with it for this class in this example here. So I am going to say our battery can be captured by something that looks like that first order transfer function that we had before, right? Where typically for a battery, when you model them in controls perspectives, right? U is your current into the battery. So this is an input current, right? It's like a current source, right? And then Y, what do you think we measure with a battery? Voltage, right? All right. Can we measure charge? Could we? See somebody nodding their head. How could you measure charge? You could. Could you measure it cheaply? Let's put it that way. Right? How does your phone have a percentage of charge? Something with the amp hours, right? Something with the capacity, that's the same thing, right? Right? But you don't actually know how much charge is going in and out. Something to think about. We'll talk about it a little bit later. Maybe if we get some time at the end of this class, right? So for a battery, we have an input current, we have an output voltage. That's what we're measuring, right? Right. And I want to get a mathematical model that looks like this. I want to find out what A and B are. I want to identify the parameters A and B such that that mathematical model, if I were to simulate it on a computer, it would do the same thing as the battery or close to the same thing, right? This is parameter identification or model fitting, right? So how could we actually fit a model for our battery? What do you guys have for ideas for this? What we need to do? Right? I have a literal physical battery I've given you guys, and I say, find me a model that looks like this, find A and B, such that that mathematical model would capture what the battery would actually do. Find the initial voltage, right? So sure, we can have some sort of initial voltage with our battery. It's going to be sitting there. We plug in our voltmeter. Okay, what do we do from there? Compare the time constants. I like the train of thought, but that's like step 5, and we're back on step 1. So we got to connect to time constants somehow. So we got to somehow connect to that. Anything? Do you think that's going to be helpful for this? Does A or B relate to the total storage? I'm not looking for a percentage, right? I'm just looking for A and B here. So you're saying to use the input current, right? And then do what with that, right? Right? So let's choose an input current and measure voltage and get some data out of this, right? So let's literally hook up this battery. So like, let's say an Arvin cycler, which is what I use, but there's plenty of ones out there, right? And let's put in an input current and find out what our voltage is out of it, right? Now you said to vary that input current, but let's think about what kind of input current we should use based off of everything that we've done in this class so far today, right? Do we want to actually vary that input current? What's an easier thing than varying our input current? We're talking experiments right now. Laplace transforms have nothing to do with it yet. right? Constant current, right? So let's take this battery, let's plug it into a charger and just say, here's a constant current going in, and I'm going to see what happens to the voltage over time, right? The voltage is probably going to increase if you're charging the battery and decrease if you're discharging it, right? So let's say we did that. Right? And we get a bunch of data points, right? Because we can't measure continuously. Right? But we get a bunch of data points that look something like that solution we already had earlier, right? This says, oh, it does kind of look like a first order system. And let's say our data points for that constant input current, whatever it was, right? Let's say at time 0, our voltage was 0 because we were reckless and left our battery at 0 volts. After 10 seconds, 2.36, 20 seconds, 3.79, 30 seconds, 4.66. Let's do 50, 80, and then 500. Right? And this is the data that we get out. These are our voltage, the measured voltage for our battery, inputting some sort of, let's say, just a current of 1. Okay, so how can this help us figure out what A and B should be? So based off of this data that we have here, what do you guys think A would be? What do you think B would be? Just give me one of them. Okay, we could, absolutely, we could do a curve fit, right? Is that necessary though, based off of, I'm trying to make this like a self-contained class here, right? So easier than that. Absolutely, you could do a curve fit, may not be necessary in this case. Yeah, what's B? B is 6, right? After 500 seconds, it's floating around 6. At 80 seconds, it was 5.89, right? It barely changed at all, right? We can see from our data, B is probably about 6 in this case. Okay, we've got B now. How do we get A? Using the tools that we have, let's hear from somebody else. Inverse time constant. Think you're on the right track here now. Now it is time for our time constants, right? So this is from our steady state value, right? Because we know if we were to apply the final value theorem, that our final value would be B, right? So what is A? Inverse of our time constant? Something relating to that. Certainly is going to be the inverse of our time constant, but what's our time constant? How do we figure that out here? Very good, right? 0.63 times B, right? What's that value going to be? Turns out to be 3.78. Okay. Then what is our time constant approximately in this case? It's about what? No, time constant, time constant. Look at our table data, right? Time constant is when we reach 63%, right, of B. Does this value exist anywhere on that table? Really close enough is what I'm going to say. It's about 20 seconds, right? So then what is A going to be? 1/20, right? So sure, we could have done curve fitting. We could have done a lot of different things here. But just using our knowledge for a first order system and what's response should be, we can take our data and parameterize our system. This is parameter identification or model fit. All right, that is it for today, folks. Have a good weekend.